go ahead and get started. Seems to be about time. Hello, welcome to this session where I'm going to talk a little bit about a case study in which a very small team of data scientists did a very big thing. We think it's big anyway, we'll see. Creating the world's smartest electrical grid in a small neighborhood, Björklinge, in Uppland, Sweden. So first I'm going to provide a little bit of background to the problem and introduce a concept that we call critical peak power. I'll present the project that was the venue for this work. I'll talk about one of the key technologies for the project, which was coordinating the operation of heat pumps. And then I'll get into the actual data science aspect of it, which was about validating a measured result. And then I'll discuss what kind of return on this invested time we got in the project. Okay, so critical peak power, what does it mean? What are we talking about when we say critical peak power? Well, here we see a graph of power consumption for a week in February. This is household power consumption, so you plug a unit into the wall and power comes out. You don't even really think about it. It's just happening all the time. And then you can see this blue line is outdoor temperatures. So this is a graph of February, so we're seeing some pretty low temperatures. And you can kind of, if you squint a little bit, you can see there's almost an inverse correlation between how cold it is and how much power people are using. So the way an electrical grid works generally is that you have a high power transmission line that's delivering power produced at some power plant to a low transmission grid, which delivers it then to your household. And when these low voltage grids purchase power from the regional grid, they generally subscribe to a power level. So you have a kind of maximum power that you should expect to draw from the transmission grid. And if it should so happen that you use too much, like right there, this is a problem. And the local grid will have to pay a substantial fee. But it's the law that a local grid must provide you with the electricity that is demanded on their net. So the problem incurs when you have too much demand than what the regional grid is prepared for. So here we come to the project VexCL. The idea here is that we should try to create some kind of smart energy community where we get together a bunch of smart resources and get them to communicate with each other and coordinate their power usage in a way that is beneficial to the grid. And for this presentation, I'm going to focus on heat pumps. And it's been really effective, we found, to deal with the problem of critical peak power by coordinating heat pump control. So this is our test bed within the VexCL project. We have partnered with a small energy grid, Upplands Energi. They have about 13,000 households on their grid, and it's located just north of Uppsala, so not really far from here. And it's a cooperatively owned electrical grid, so it's a bit different in that respect, and that's kind of a unique aspect of this project. You might be wondering, what is an Ngenic? It's the company that I work for, and we're a part of this VexCL project, but we're also the makers of this product, which we call Tune. And basically, it's a unit that you can augment your home heating system with that provides a higher level of thermal comfort and provides you with some extra functionality via a smartphone app. But we found that we can also use it to organize the operation of heat pumps in a smart energy community that we want to try to create. Okay, so rewind back in time, back to February. It's getting cold. This guy is out walking around, and we sort of see that, okay, we want to do this smart community, and we want to try to make this intervention in this project, in this test bed, and see if we can't keep these critical peaks from occurring. Okay, so that happened, and then a few weeks later, temperatures are no longer critical, our intervention has been implemented, and now we have a data science problem. So looking back, you have this curve, household power usage over time. It's a time series, and we want to figure out, is it lower, is it different, is it higher than what it should have been? So when you talk about trying to compare something to what it should have been had you not done something, this is a modeling question. So here we have these vertical orange lines, and that indicates when the Ngenic load shifting technology was in effect. So we basically identified, between 7 and 8, we think there's probably going to be one of these critical peaks. So, okay, we send out a control signal to our heat pumps. Now we want to look at the aggregated power use of the entire net and see, was that enough to make a difference? Can we actually motivate somehow the fact that something happened? So rule number 1, step number 1, get to know the data. So the first thing we do is this, what we call Stl Decomposition. It's classic time series analysis. You get a computer program to do this, and it takes the combined signal that's this up here and breaks it into various components. We have a seasonal component, which pretty obviously has a daily periodicity, or twice a day, one peak in the morning, one peak in the evening, one when people are getting up and making breakfast, and another when they come home from work and start cooking food. Then we have the long-term trend. This could be something that coordinates or correlates with temperature, for example. And finally, we have just the remainder, which is basically white noise. And notice here that the amplitude of the noise is important. Between -6 and 4 megawatts, that's quite a lot of noise for the heat for our model to try to be able to predict. Okay, so we want to build this model that can predict power consumption. We remember that we have a correlation probably with temperature, and we see that we have this daily periodic structure that we want to try to exploit. So our idea, we want to create a bunch of features that capture this periodicity and temperature dependence. So we basically start by something like this. If anyone can read R code, I guess it's not a good idea to have code on the board, but I suppose you understand what it means. Breaking things up into every minute of every day, so each sort of time unit gets a dummy variable so that all those who belong to the same unit get that variable. We want to create averages for each of the dummy variables so that for each minute of each day you have an average temperature for that time period, and so on. And you end up with a massive set of features that hopefully somewhere in this maze capture the structure that we want to be able to exploit. So given that you have a bunch of features in this data, and you now need to choose a model and a permutation of this huge feature space, and compare these with some sort of metric, such as the mean squared error is a good one for this application. So here we're comparing data points as predicted and data points as measured. And 0.2 megawatts is pretty good. It's substantially less than the noise factor. So now we make this model prediction. You can see the blue is our modeled prediction of what the power should have been given temperature and time of day conditions. Here's the time period of the intervention, and the red line is the measured power. So, okay, we have a prediction, but really the prediction by itself isn't really enough. We need to do something that can capture the variance of our model. And so this is my favorite algorithm, and you probably recognize it. It's the bootstrap. It's amazing. Of course, I won't go into super much detail here, but this letter B, that's a number, a large number, and basically what the bootstrap says is that for each point that you want to make a prediction for, you take a sample, you resample your data with replacement, and train a new model on it, and make a prediction based on that model. And you do that B times for each point. So in this application, I think we used B equal to 1,000. So for each modeled point, we use 1,000 models. And then you can sort of approximate a confidence interval by taking the quantiles of the set of predictions for each point. And that way you can get these confidence intervals that sort of capture the variance of your model. So on this plot, when you plot it, you can only see the lines, but actually each sort of consists of points. So behind each one of these points is a set of 1,000 models, and this sort of describes the distribution as seen from above, if you can visualize it that way. So if we do 20 data points, that's 20,000 models. The next step is to sort of distill these models into some kind of number that means something to whoever is your client in the situation. And in this project, we're sort of working towards trying to validate something that the grid owners have seen in their own data. So we distill it into energy. We take the integral between these two curves, and we get a number for energy that results in some numbers. And a lot of times, 20,000 models all comes down to a table of, 6 numbers. And this is presented to whoever is the sponsor for your project, and you sort of hope that it makes sense for them. And in this situation, it actually turned out quite well for the project. We were able to present these numbers to Upplands Energi, and they can sort of check against their own measured data and see, is this something that makes sense? Is this a figure that we feel could be reliable? And in this case, it worked out pretty well for us. And in the end, the return for this investment of time ended up being a commercial agreement with Upplands Energi, and also resulted in this prestigious award, the International Smart Grid Action Network, which is a project within the International Energy Agency, gave us this award of excellence that we covet. It didn't really come with anything else. There was no cash prize or anything, but we got this glass thing. But we're very proud of it. So anyway, that concludes everything that I wanted to say. And thanks for your attention.